Good evening, everyone, and it's a great pleasure and privilege to have been invited to deliver this year's Sir John Charnley lecture. The Royal Aeronautical Society, under the leadership of Sir Brian Burridge, is focusing on two particular areas at the moment. So one is the sort of green agenda, more efficient aircraft, more electric aircraft and so on. And then the other key topic is autonomy. And there's a very interesting intersection actually between those two in areas like electric urban mobility, where people are looking at small passenger craft capable of going small distances using electricity. But what I'm going to concentrate on tonight is the topic of autonomy. And what I want to do is share some of the learning, some of the lessons that we've had as we've started to push the boundaries of technology in autonomy. And also to really signal that we need perhaps a degree of caution. There may be one or two speed bumps ahead. This is harder than you might think. So I'm going to try and set out some of the themes I think are important for making sure that we can deploy autonomous systems at scale, but do it safely and affordably. The complex socio-technical systems tag on that slide really is just the kind of things I'm talking to universities about now. Essentially, that means how do humans interact with complex systems, and what are the ways in which that can go wrong, as sometimes it will do, and you'll see some of that through the talk tonight. I thought I would start actually by talking about Sir John, because obviously renowned for the work on blind landing and the blind landing experimental unit, and the work that was pioneered by him and his colleagues really has been enduring. It's important today just as much as it was then. But there are a couple of things in particular that I want to draw out from Sir John's work, because they're very relevant to what I'm going to talk about. And that was really the way they went about developing what was one of the first automated or autonomous aviation functions out of blind landing. So the first key point to make is they had to decide how safe did they want this to be. And they used a concept which is very important, really, of saying, well, it should be equivalent safety. Why don't we make it at least as safe as the equivalent manned activity? So if on average a manned landing in good visibility achieves a certain level of safety, let's make it 10 times safer to add a bit for luck, but let's use some sort of notion of human equivalence as a reference point for that safety target. And I'll return to that in the context of autonomous cars as well as autonomous aircraft. Having done that, of course, you now had a safety target which is so stringent that you have no possibility whatsoever of demonstrating that you're meeting that safety target experimentally. It's got to be done by analysis. You can only do that if you then decompose that safety requirement into subsystem requirements and different functional requirements, and then demonstrate that you've met each of those requirements, add it all back up again, and demonstrate that you've met the safety requirement. And that sort of approach, that statistical approach, has been at the heart of really all aviation safety cases that we've had since those times. And it's that type of thinking and that type of rigorous analysis of those probabilities that is the reason why manned aviation is so safe, why aircraft don't crash very, very often. So these approaches have been pivotal. They're just as relevant today as they were in the time when Sir John was pioneering these things. But there are some things that have changed a bit since those days, and we need to augment those approaches. In particular, software has got more pervasive and more complex. When you start looking also at the way in which human beings interact with these complex software systems, actually these statistical, reductionist, hierarchical approaches don't always work too well, and I'll show you some examples of where that can go wrong and why we need not to replace the kind of things that Sir John did, but actually add to them with things that are more centred around software and around human beings. I thought I would put a quick slide up on me as well. So as was mentioned, I've just retired at the end of last year from Thales. That's probably one of the most exciting and technologically advanced companies I've ever worked for. So you'll forgive me if I put a few shameless plugs in during the course of the lecture for what they do. But I've worked on a number of things, starting with naval decoy systems, working on space space systems, working for a company called Astrium, now part of Airbus Space and Defence. I developed a lot of the work around the Typhoon aircraft, particularly the Defensive Aid Suite. I've worked in civil aviation. You can see a little general aviation aircraft there. And then more recently, bottom right, tactical UAV systems. And what I'm going to share with you tonight are some of the insights that have come from those things. I put this slide up for two reasons, really. One is that for those of you in the audience who are, shall we say, my vintage, you don't need any persuasion at all that aerospace is a fantastic sector to work in. But for the youngsters out there, it really is a fantastic sector to work in. It's full of the most interesting challenges, really cool technology. It's well rewarded, so it's a really good career choice. But the other serious point I want to make off this slide is that a lot of my career was involved putting stuff up there and then figuring out why it's not working properly, and on occasions why it's come down again when it wasn't meant to. And particularly if you've flown in an experimentally certified aircraft while you're trying to debug a bit of safety critical avionics and figure out why it's not working properly, you get a real sense that the system and nature are out to kill you. And you get really obsessive about understanding every anomaly that you see and running it to ground, because it might just be a blip on this flight, but it might kill you 10 flights downstream. So I've developed, I think, a fairly healthy paranoia about aviation and the things that go wrong in aviation. And I've certainly taken that into the way I've looked at autonomous systems and some of the issues there. I think it's an important point to make, because if you look at autonomous systems and urban air mobility and things like that, what we're seeing is loads and loads of organisations and people flooding into that because they think it's going to be a huge market, it's going to grow explosively. Many of them don't have any aviation experience at all. They don't have that aviation instinct or the aviation culture. And that's not necessarily a bad thing, but we need to think about how we instill those kind of cultural norms into those new organisations. And again, that's part of this sort of socio-technical systems agenda that I'm looking at. I said I would plug Thales and plug the UK, so I will do that. The UK is actually a great place to be working on autonomous systems. There's some great technologies around. It's not just airborne stuff. You can see on this slide pictures of surface autonomous vehicles and underwater autonomous vehicles and stratospheric blimps, but also in non-aviation sectors, so autonomous trains, autonomous cars, and the simulation on the bottom right-hand side actually is an autonomous car example of work that we were doing with Warwick, which is interesting because it's not just trying to simulate the car and the autonomous driving algorithm, but it's also trying to simulate how the human beings in the environment will interact with those things, and how do you try and simulate not just the technology, but also the people. And you won't be at all surprised to find that simulating people is actually the hardest bit of the challenge. We also, as Thales, operate a couple of test facilities, national assets, so one in West Wales, which is a very important base for flying unmanned air systems. And we also recently opened a facility down in Charnley Wharf, which is designed to allow for experiments with surface and underwater autonomous systems, but also with airborne systems involved as well, so you can do the complete networked autonomy exercises. And it's not just about doing things in specific test ranges and danger areas. So again, this is some footage from the end of 2018. This is actually a flight over the centre of Helsinki. So you're now seeing drone operations in urban populated areas being conducted safely, in this case using a UAV mission planning software tool called Horizon. And I've put the link down at the bottom. You can get your credit card out, you can go and sign up and get access to this. I'm afraid I don't get a commission, unfortunately, but that's there, that's live now. And then coming to the title, of course, we are on the cusp of an explosion in these kind of technologies. Yeah, we're expecting to have these things buzzing around all over the place. People will have seen things around Amazon Prime and all the rest of it. Urban air mobility is getting a lot of attention at the moment. I couldn't resist putting the picture of the Aston Martin concept up there because it just looks so good. But other manufacturers' offerings are available if you choose. But the slight note of caution I want to raise here is that the technology is racing away, but it's going faster than our ability to produce safety cases or to produce regulation or to demonstrate these things when deployed in the real world at scale will be as safe as we want them to be. So I'm not trying to be the guy with the red flag who had to walk in front of the first automobiles. If you remember that, we thought they were so dangerous, somebody had to walk in front with a red flag. Okay, so I'm not that guy for unmanned air systems. But it's a serious point. We've got to think about what's proportionate, what's effective, what's affordable if we want to do this safely at scale. And what I want to do is signpost some of the things that we'll have to think about as we go on that journey. So this is the essence of my lecture tonight. It's my 3 things to keep in mind on autonomous systems. So my first point is that the software, hardware, and what I call the wetware, the human beings, will go wrong in all the same ways they already go wrong in manned aviation. Okay, so let's not forget what goes wrong and that it will apply in unmanned aviation just as much as in manned aviation. I'm going to give you some examples of that. But my second point is that actually the hardware, software and wetware will go wrong in new and interesting ways in unmanned aviation, and I'll give you an example of that. And then finally, and this is really my main socio-technical systems soapbox, peeve, unmanned systems are not unmanned. Okay, there are people involved, whether it's in the design or the operation, deployment, whatever. And if you think they're unmanned, you've just done a poor job of systems engineering. You've drawn your system boundary in the wrong place. And again, I'll give you an illustration of that. So a couple of caveats that I have to say. So the first one is I'm going to illustrate my talk with some real crashes because I think that makes it more interesting. But obviously any crash is a sequence of events. It's a very complex chain of events. So I'm selectively picking things out to make points. If you want to look at the authoritative, definitive account of those accidents, go and look at the service inquiry reports, which you can find online. And obviously I'm talking for myself, I'm not talking for the companies or the MOD organisations involved. Secondly, I wanted to mention an initiative that has been taken under the auspices of the Defence Suppliers Forum. So my boss, Victor Chavez, the CEO of Thales UK, spoke at the first International Defence Safety Conference 18 months or so ago and said, look, we're a bit concerned about safety for unmanned air systems because we think that for the amount of money we've spent on safety work, both internally and in the customer community, we're not getting the results we would have expected. We think that people, when they crash stuff, will get a bit shy and don't really want to talk about it. But if there's one lesson that we should take from manned aviation, it's that the most important thing is to openly share the insights that you get from things that go wrong. So could we do more of that? So what Victor basically called for was players in the industry. And by the way, everybody who's flying big UAVs has crashed. Okay, you know, Thales is not unique in having crashed a couple. Everybody that's doing this stuff has actually crashed. Let's get those people together, share the experiences and see if we can come up with some insights that will help us map out this roadmap to a safer deployment of autonomous systems. So that initiative kicked off. One of my colleagues, now that I've retired, is taking that initiative forward. A guy called John Meston unfortunately couldn't join us tonight, but I have told him his name is on the slide. And please do contact him if you're interested in finding out more or contributing to this initiative. And during the course of this year, the aim really is to produce a handbook, a body of work that says, here's stuff you might want to think about if you're developing and operating UAVs. And then my final caveat really is just to say that hindsight's a wonderful thing. So some of the things that I'm going to say will seem quite simple. But let me assure you that things that are simple can still be not obvious at the time. And the other reason I'm keen to talk about some simple things is because I think that way the learning will actually spread. It's much easier to spread simple lessons than really, really complicated ones. So some of this might seem quite simple or even trivial, but actually it's quite profound. And trust me, there are a lot of very, very smart people involved in these programs. So things can be simple without being obvious. These are the folks that are involved. You'll see actually a couple of local heroes, if I can put it that way. So Blue Bear, just down the road, and obviously Cranfield have been involved in this work. as well as the universities of Southampton and Bristol, which I've already mentioned, and a number of other players. So while I'm going to illustrate my talk with some of the issues we experienced at Thales, that's just because they're the ones I know best and I can talk most clearly about. But the direction of travel, the key themes that I'm going to talk about, really have come from this group of people sharing their experience in a very open way, which I think has been a really good initiative. Before I get into the detail, though, I just want to tease apart a slight distinction between what we mean by automatic systems and what we mean by autonomous systems, because we tend to use these terms relatively freely, relatively interchangeably, but there are some important differences. And in particular, my distinction between automatic and autonomous is that the automatic system, so this is where you have a system where you say fly from point A to point B and arrive at this time and do it minimizing the use of fuel, for example. That would be automatic to me. If it's autonomous, it might be go and survey an area over there and report back if there are enemy tanks, but don't give it too much direction as to how to do that. Now, clearly, as you go to more autonomy, the system's capable of deciding what to do, and the commands that you give it tend to have a higher degree of abstraction, which is very powerful, but if it's a higher degree of abstraction, also it tends to be more ambiguous, and it's not always as easy to tell whether it's doing what you intended. So autonomous systems, to some extent, behave as though they have free will. I should say, by the way, I've been taken to task over this slide on a couple of grounds. So one is that I think automatic systems are more deterministic than autonomous systems. I was taken to task by DSTL, who said, no, it's all software, therefore it's all fully deterministic. Your point is wrong. What I really mean is, from a practical level, the automatic ones are deterministic enough that if we repeat a test on it, we give that system exactly the same stimuli, we'll get the same result. If you've got an autonomous system that has learnt from experience, you could repeat a set of stimuli at some point in the future and get a different outcome. It's deterministic in the sense that if you put in all of the learning experiences that it had had, yes, you get to that same place. But from a practical point of view, it's behaving as though it's got its own mind, it's making its own decisions, it's got free will. The other area where I've been taken to task is in talking about free will, and my advice to you is never try and have an argument with a philosopher about free will. So my stepson has a degree in philosophy, and what you have to understand is that arguing with a philosopher is like wrestling with a pig in the mud when it's all slippery and difficult to hold. It's completely futile, and the pig enjoys it. Okay, so don't bother. So this is the key point. One is very deterministic, the other is less deterministic. All of the certification approaches that we use at the moment, which consist of breaking the system down into little bits, testing them, showing that they do what they want, adding it all back up again, rely on it being deterministic. And when you get into something that's genuinely autonomous, that has learning capability, those approaches are less effective. And that's underpinned really the journey that this Defence Suppliers Forum work group that I was talking about is on. So we've kind of got three themes here. We've said we're on a journey from manned systems to automated systems to genuinely autonomous systems, and it's getting harder as you go towards the right-hand side. And I've paraphrased the famous Donald Rumsfeld phrase about unknown unknowns to say really the three areas that we want to look at are what I've called new known unknowns. We now know if we're going to certify autonomous systems, here's some of the stuff that we've got to be able to deal with, but we don't actually know how to do it yet. And that's really to try and guide the research agenda, and I'll talk about a couple of research topics towards the end. In the middle, we've got the automated stuff, where actually now we know quite a lot about what's needed, but it's not necessarily in the certification approaches that are used today. So that middle strand is about making sure those insights get captured in the certification approaches. And then Rumsfeld didn't say this, but I've extrapolated. So on the left-hand side, we've got the shoulda knowns, where we've got experiences from manned aviation or knowledge that we've already got that we just didn't act on. So that's really about, can we improve operational safety today, what we're doing today by sharing the knowledge. So those are the three strands that work group is looking at. And my talk will broadly follow those three areas. So let me pick these three laws apart, and I'll give you some examples, hopefully, which will make my point. So let me start with stuff will go wrong in just the same old ways that it goes wrong at the moment. So this is a picture of something which I think we could agree is a manned aviation experience going badly wrong. So this is in Frankfurt. This is an airliner that's gone off the end of the runway. And it's gone off the end of the runway because of a safety feature. So people decided that, generally speaking, when the aircraft was in the air, it's probably a bad idea to engage the thrust reversers. And I think we would agree that seems like a sensible safety feature. But of course, if you've landed and you need reverse thrust, but the aircraft weight on wheels system hasn't worked properly and the aircraft therefore doesn't know it's on the ground, you can't get your thrust reversers. There are other incidents like this in some cases where not only have they engaged reverse thrust, but they've whacked the throttles open as well to get maximum braking without realising that that's just taking them off the runway even faster. So that's just an example of stuff that goes wrong in manned aviation. And here are two examples of where exactly the same thing has gone wrong in unmanned aviation. Two cases here. So one is weight on wheels hasn't worked correctly and the aircraft therefore doesn't behave in as controlled a fashion as you would like. In another one, because it was a bit bumpy and there were some other system malfunctions, the system thought it was on the ground before it had actually reached the ground. And the disadvantage of that in this case is that the braking manoeuvre is to apply full nose down to get as much traction on the runway. And of course, if you apply full nose down when you're above the runway, it tends to end badly. So that's a very simple example where a problem that's known in manned aviation has transferred basically unchanged into unmanned aviation. This is another one. So the left-hand side, sorry, these are a bit fuzzy, but the left-hand side is just showing the ground track out of West Wales Airport. And the right-hand side is the classic sort of James Reason Swiss cheese model of the set of events. So you don't need to read all of that. The key point is really at the bottom. Again, if you go back to Sir John's work, that demonstrated that you couldn't meet these kind of high levels of safety, the 10 to the minus 7 or whatever, without redundancy. So if you have a flight computer that is 10 to the minus 4 per flight hour reliability or something, and you need more than that, you put two of them in there, multiply the probabilities, jobs are good. The problem on this particular case, and it's not in any way unique to unmanned air systems, was simply that the redundant computer was in the wrong state. So when the primary flight computer failed, which will happen from time to time, and switched over to the backup computer, nobody's flying the aircraft. And again, that doesn't end well. So the key thing here is not that it was unmanned, it's just that the redundancy architecting in this case wasn't effective. And that's a really, really important point that I want to emphasise, because in going to unmanned air systems, we're still likely to need redundancy to meet the safety targets. But because they're small, cheap systems, you don't necessarily engineer those redundancy architectures with the full rigour that you would have on a passenger aircraft. And if you get that wrong, it will come back to bite you. And it bites you because the errors are really big. If you make a mistake in redundancy architecting, your reliability claim, your safety claim, isn't wrong by 10 or 20%. It's wrong by 3 or 4 orders of magnitude, okay, which is a pretty non-trivial error. So those are a couple of examples of my first law of unmanned air systems. Let's go on to the second one, which is about things going wrong in new and interesting ways. And I'm going to talk about pitot tubes. And pitot tubes have been on aircraft from the dawn of aviation, really. I'm sure with this audience I don't need to explain what a pitot tube is, but basically you're measuring the air pressure due to motion, half rho v squared, etc., etc. If they get blocked, you don't get the right answer for your airspeed. And I've given you a couple of examples of blockages there. The most normal one obviously is ice, but also insects do like to go and burrow into them as well, apparently. Now, pitot issues have been causing aircraft to crash, as I say, from the beginning of manned aviation. But it doesn't actually happen that often. The reason it's a nasty effect is that it creates a positive feedback condition. So if you think about an aircraft that's climbing, which is going to be tending to slow down because it's going uphill, but the static pressure is dropping, so you think you're going faster when actually you're going slower. And if you're descending, it's the opposite. As you go down, the static pressure gets higher. You think you're going slower and slower, despite the fact you're going faster and faster. And because it creates a positive feedback condition, if you're in a manned aviation system, a passenger airliner, and you have a Pitot problem, the first thing that happens is the autopilot disconnects, because otherwise you'd have a positive feedback condition, you'd go into a runaway dive. So the autopilot disconnects, and the instructions to the pilots basically say something on the lines of, don't do anything stupid. Okay, just keep it level, stay calm, don't mess about with it, and it will sort itself out. Let the pitot heating work on the ice or whatever it is, you'll be fine. There have been some cases where the pilots lost situational awareness that ended very badly, but generally this is not a critical incident, it's survivable. But what if we've got an automatic or autonomous system? We tell them to fly from point A to point B. We don't have the ability to disconnect the autopilot. So if you have a control loop with a positive feedback condition, funny old thing, you get oscillation. So this is an example of that phenomenon. We've had a Pitot blockage, or dual Pitot blockage, in fact. And what you'll see on the right-hand side is what looks like some fairly dirty sine waves, but roughly speaking, they're sine waves. Those are sine waves in altitude and sine waves in airspeed. And what's happening is the system is trying to go into a runaway dive under the autopilot. There's a safety mechanism that says if it looks like it's all going badly wrong, try and pull up and give it some power and all of the rest of it. So it's starting to run away, it's recovering with an emergency mechanism. It's not learning anything by that process, it's just an automatic system. So it just repeats. And unfortunately, every time it's coming over the top of one of these humps, it's very close to stalling speed. So after a while, inevitably, something knocks it off its perch, and the last 3,000 feet of this particular flight trajectory were more or less vertical into the sea. So this is Pitot blockage. I mean, we've had Pitot blockage since the dawn of manned aviation, but we haven't really figured out that if we can't disconnect the autopilot, it's going to be in a very difficult situation. The right-hand graph here just shows the elevation profile. So in this particular mission, it had climbed up to some quite high altitudes. It was about -8 degrees, descended back down. It was very wet, etc., etc. And you can see on the right-hand side of the slide here, this period where it's just in a sinusoidal oscillation, changes level a little bit, but then finally just tips over the edge. One of the interesting insights from this is that the safety case work that's required for autonomous air systems at the moment really doesn't address what happens when it all goes horribly wrong. So it builds a safety case that says we can never have a dual Pitot blockage, and if we did, it would be game over. But didn't really say, well, what really happens if that occurs? What should we simulate that? Should we see what kind of behaviours we see? And how do we try and recover the situation? And what kind of degraded capability does the system have? Because the other interesting thing in this case is the altitude that the aircraft is oscillating around isn't the commanded altitude. It just happens to be where the Pitot tubes froze. So if we're now trying to construct recovery approaches, backup scenarios, we need to understand that we can't control vertical altitude anymore. We can control it laterally, but we can't control it vertically. So we need, I think, to move away from this very kind of black and white certification approach that says it either works or it doesn't. So I think something that says, as it's going wrong, what are our options to try and recover it safely? What degree of controllability have we got? And something that's much more nuanced. Because in many cases, these sorts of scenarios would be recoverable had we known what was going on or had we anticipated the effect. And I talked about simple lessons. So here's a very simple lesson for you. Clouds are wet. No, they're really wet. When we talk to people about this, there's a view that cloud droplets and things like that, they're so small they'll get swept past the pitot tube and all the rest of it. And they don't. At the kind of speeds we're talking about and the droplet sizes we're talking about, we reckon that from about 3 microns up, pretty much all the water goes down the hole. And that means in a cloud, typically 10 microns at least and up for droplet size. Pretty much all the liquid water goes down the pitot tube. And therefore, if you can't clear it through effective drain systems or heating, it's going to accumulate. I did a back of the envelope calculation. That is literally the back of an envelope, by the way, which I scanned in. That says, well, if you've got a cloud, 0.3 grams per cubic metre, something like that, how long does it take to get enough water to create a droplet that blocks the capillary tube if you're flying in cloud? And the answer is it's something like 15 minutes. It's not very long at all. Now, if that drop then freezes, it's kind of game over. If it's just liquid, they tend to form and then break and then reform. So you get little pressure pulses building up. And that's one of the bits of good news. It's a really, really easy early warning sign to pick up. One of the great things about unmanned air vehicles generally is they have a huge amount of instrumentation, huge amount of data. And what Thales does now is it's looking at the data feeds for every flight, looking for anomalies, so you can pick up these early warning signs that something might be going wrong. Again, that's not required really in the approach to certification at the moment, but it's clearly a very desirable thing to be doing. The other lesson from this is that you've got to be, again, really careful about how you do your redundancy architecting. So in this particular case, there are 2 dissimilar pitot tubes. Okay, so we've got redundancy, we've avoided common mode hardware issues because they're completely dissimilar. But of course, if they're both in the same cold, wet environment, their behaviours must to some extent be correlated. And therefore, your claim that they're completely independent must be degraded. And again, as we saw with the flight computer case, degraded here means by several orders of magnitude. We're not getting this 10 or 50% wrong, it's several orders of magnitude, so it's really quite significant. And it's sobering just to think that rotary wing UAVs, it's obviously different. It's in a sense a much easier problem. But anything that's fixed wing, that's using what you might have thought is the obvious technology like pitot tubes and those kind of things, actually are vulnerable because they fly slow, they fly low, they could be in bad weather for a long period of time. The bore in the pitot tube is quite small, so surface tension, capillary forces are really quite important. You can't just use ground speed as an alternative because often the wind velocity is a significant fraction of your airspeed. So ground speed isn't that useful. And you can't disconnect the autopilot. So actually it's quite sobering that we've been bitten by something that you would have thought was just transporting across from centuries of pedigree in manned aviation, but actually it's bitten us along the way. So let me go on to the third of my main points, which is about unmanned systems not being unmanned. And again, I'll give you just a very simple example. But before I go into the air, I thought it was worth talking about automotive quickly. So you're not expected to read the fine print here, but this is from the Society of Automotive Engineers. And if you look at what's been going on with autonomous cars, there was a very appealing roadmap painted for how we were going to get to fully autonomous cars. So you start at level 0 where you've just got very basic driver aids going through cruise control and lane control and things like that, all the way up to level 5 where you don't have a steering wheel, it's completely autonomous, you just get in, it takes you where you want to go. And it's quite appealing. It sounds like a kind of linear process where you just pour more and more sophisticated technology in until you get to the end state that you're after. But the detail's quite important. There's this little blue box that you can see at level 3 that essentially says when it all starts to go wrong, the human being takes control. Okay. And this is a classic example, I think, with my socio-technical systems hat on, of people like me, technical people, designing systems with a view of how we would like the humans to behave, rather than designing them with a view of how humans actually behave. And if you look at research that's now been done about this, including at the University of Bristol Robotics Lab, if you've got your human being sitting there looking at a video, doing their email, snoring in the seat or whatever, and the automatic system can't cope and they have to take over, by the time they've regained situational awareness, they've closed the feedback loop around the steering and the brakes and everything else and processed what's going on and taken the correct action, you're talking about 10 seconds or so to get from that switched off, not engaged state to in control. And I would argue that 10 seconds is a very, very long time if you're driving down a motorway or a dark B road at night or whatever it might be. So there's a real issue in that middle. And I think what's been missed is something that was presented as a continuum actually has a human-oriented discontinuity right in the middle. And we're struggling to understand how to deal with that effectively. And we've seen the kind of outcomes that we get from this. But it also allows me to link back to Sir John's work again and say, well, how safe is safe enough actually? And Sir John started with the concept of equivalent safety. We want it to be as good as a human or maybe a bit better than a human. But actually what we've seen with autonomous cars is that public opinion don't really buy into equivalent safety. The bar is set much higher. So if Google or Uber or Tesla crash one of these things, it's headline news around the world. But annually, according to the World Health Organization, more than 1 million people a year die in road traffic accidents. So if we deployed this technology globally, I think it could make a huge impact on road fatalities. But at the moment, we're trying to set the bar so high that just a single event is a problem. So again, I think that's one of the challenges we have with the unmanned air systems world, is how safe is actually going to be safe enough. And again, I think 5 or 10 years ago, people thought as good as a human was good enough. I think the bar is going to be set actually in the real world much higher than that. So this is a joke that navigators seem to like for some reason, but there's an old joke, right? What's the cockpit of the future going to be? It's a pilot and a dog. And people say, well, why is the dog there? The dog's there to stop the pilot touching any of these complex software systems and screwing it up. So people say, well, why have you got the pilot? Well, he's there to feed the dog. Okay, so it's an old joke, but it's a good one. But the serious point here is the job has changed. The history of unmanned aviation, UAVs and so on, has been littered with a desire to label things as RPAS or RPVs, remotely piloted air systems or remotely piloted vehicles. Actually, I think that's been really, really unhelpful. I think it was done to try and reassure people on the ground. There's somebody flying it, don't worry, it's okay. They're just remote. What we've missed is that the job is different. I'm not saying that having an aviation or a piloting background isn't necessarily a good thing, but the job is different. We're talking about people that are operating and supervising really complex automatic software systems. And the key issue is to understand how they behave and how they go wrong and what kind of countermeasures you might take to the failures. So the job is wrong. The job needs to be defined properly. It's not necessarily remote piloting. The other comment which I added as a result, following a conversation actually with Nancy Leveson, who I will talk about in a moment from MIT, she said, and to take the blame when it all goes horribly wrong. We need the human there to take the blame. And the example I'm going to show you in a moment, I think, in a sense, suggests we haven't learned enough from manned aviation. So if you go back to the beginning of manned aviation and aircraft crashed a lot, nobody was that surprised because it was all string and sealing wax and baling wire, and if it fell apart and crashed, nobody blamed the pilot, right? The aircraft was just the thing that was at fault. And then we put all this really clever software and systems into the aircraft and said, well, our systems now are so good that if it crashes, it's obviously the pilot's fault. And we tended to blame the pilots a lot. Kind of glossing over the fact that they probably didn't go to work that day determined to kill themselves. The decisions that they made in the air at the time were the ones that they thought made sense. And then we became more mature and realised it's a systems issue, it's a systems problem. And what you have to think about is how do you make sure that the pilot can interpret what's going on, they don't get overloaded cognitively, etc., etc. And we did get into that systems thinking. But in unmanned, we've been very quick to go back to the dawn and say, well, if it goes wrong, it's the operator's fault rather than a systems problem. And I'll give you an illustration. I mentioned Nancy Leveson. So Nancy is one of the world's leading researchers on these kind of safety critical systems, and particularly the human interactions with them. She's written a book called Engineering a Safer World. There's a lot of stuff on the MIT website that if you've not come across it, I commend to you. I think it's very helpful and useful. So this is a slide I've stolen from her that just makes the very simple point that most of the safety approaches that we use today have come from an era of complex hardware. They've come from the era that Sir John was working in when they were developing the original blind landing systems. And broadly speaking, we assumed that things went wrong when something broke, a component broke. It's all about hardware reliability. But of course, in recent years, we've seen an explosion in software complexity, and the actions that the humans have to take in the cockpit or on the ground have become overwhelmingly more difficult and more complex. And we haven't really augmented the set of safety tools adequately to deal with that fact. So that, I think, is one of the really urgent things that we have to do if we're going to deploy unmanned air systems at scale safely. And I'll illustrate that with a very simple example here. So this is a picture of a tactical UAV where it has not ended well. And this is a true statement here. You know, if the operator hadn't cut the engine, it wouldn't have crashed. So everybody says, stupid operator, you know, slap them around the head, train them better, you know. No, it's a systems issue. That was the right decision in their frame of reference at the time. It wasn't a stupid decision. We have to look at why that seemed to be the right decision. So let's look at that in a little bit more detail. So there's two pictures here. Sorry, they're not very clear, but hopefully you can see on the top left there the runway centre line. The aircraft's coming in from the top right-hand side, touches down, doesn't get ground touch, by the way. That wasn't a major issue, but it's interesting that that's happened again. And it deviates off the centre line of the runway till it's at the edge of the runway. And actually there's a bit of a habit at this airfield of it doing that. So the operators have kind of got used to seeing it do that and then sort itself out. So they don't react initially. So there's some reaction time that's lost just because people have got used to the way a system behaves, even though the way it behaves isn't quite what it's designed to do. And then at this point here, some really critical stuff happens. So the aircraft is smart enough to know that this isn't going well. So the aircraft decides it should take off and go around again. And if it had been left to its own devices, it would have taken off and gone round and come back and landed again, and that would have been fine. But the operators now see it on the edge of the runway going onto the grass, so they tell it to take off, you know, abort the landing, take off and go around again. But because it's already decided to take off and go around, it doesn't respond to their request for it to take off and go around. So the operator's mental model now is it's on the grass, it's under power, it's not responding to our commands to take off and go around. What's the safe course of action to take in those circumstances? It's to cut the engine. That's a perfectly rational decision to take with the information that they had available. Unfortunately, because the aircraft decided to take off by itself, it's now in the air when the engine's cut and it glides over the B road and lands up in a tree. Now, the other interesting thing that came out of this is the picture on the right. So this is an iStar asset, so it's got a camera on it. And when you land, you turn the camera backwards because you don't want stone chips and things like that on the lens. So this video feed serves no purpose at this point in the mission, but it's there. And on that rear-looking camera image now, what you see is grass under the aircraft. But of course, you've got no real depth perception. It's all blurred, it's going past quickly. So all you really know is that you're over the grass. Now, the safety architecture says we will completely compartmentalise everything to do with iStar from everything to do with safety critical flying the aircraft, quite rightly, because you want to be able to change the I-star payload without worrying about recertifying the safety critical software. But from the operator perspective now, they have an image which is nothing to do with flying the aircraft officially, that encourages them to take an action which proves with hindsight to be the wrong action. And again, in this issue of trying to decompose things and get redundancy, of course, we haven't really got any statistical benefit from having more than one person there, because human beings with the same training, confronted with the same stimuli, are going to tend to come to the same conclusions. So again, we've not really got much redundancy in a practical sense here. So I think that's quite an interesting one, but I was, the bit that says it's the operator is so missing the point. This is a systems issue, it's a socio-technical systems issue, and we need to think about how we design the systems so that we get better outcomes. So if you only take away one thing tonight, I'd like it to be this slide. And this is my attempt to summarise these points. And what I'm really saying here is there are three critical perspectives that you should bear in mind if you're designing and operating unmanned air systems. Clearly, you want to do a really good job of designing it, and that's the green blob. Design it, certify it, do all the good stuff that we know how to do. But then you also have to recognise that either because of environmental effects or because there's a failure in the design or it's under cyber attack or whatever, what it's actually doing might be different. And then if you've got a remote operator, and because they're remote, they've got limited observability of what's going on, they've got limited ability to control the aircraft, what the operator thinks is going on is also important. And my argument is that if what it's designed to do, what it's actually doing, and what the humans think it's doing are all different, there is at least some potential for things to go wrong. So how do we develop a portfolio of certification and safety tools that make sure that those perspectives don't diverge? Oh, and by the way, when you throw in some machine learning, it gets even harder, because now not only can the humans learn bad habits, but the machine can learn bad habits as well. So that for me is the essence of the challenge that we face in the next few years. So just to summarise quickly how that's sort of played out in this cross-sector initiative that I mentioned with the other players involved. Here are some of the things that we've come up with. So from a point of view of improving operational safety now, we've said, no great surprise, things like probabilistic risk assessments and common mode analysis, we need to be a bit sharper on that. We need to think about the human factors issues in designing these systems. And we also need to think about what I've called operational risk assessment here. Because what we've done in unmanned aviation is essentially port across all of the stuff that's been done in manned aviation that's worked really well. And that's fine, but most of the stuff in manned aviation is predicated on not killing passengers. You don't want to kill the airline passengers if you have an issue. So the whole approach is really about making sure the aircraft doesn't fall out of the sky. Whereas with an unmanned air system, what you're worrying about is who does it land on when it does fall out of the sky. And if you just think about this in really simple ways, you could do things like don't fly that mission crossing a rush hour motorway. Fly it an hour later if you can. So you've changed the risk profile, not by changing the design, but by changing the way that you operate. And that, I think, is something that the regulations don't really capture adequately at the moment, and is a really quick and easy thing to do, by the way. And then in the middle, we're talking about how do we bring these kind of more human-centered approaches, so the sort of systems theoretic approaches that Nancy Leveson and MIT have developed is one example. There are others. How do we make more use of model-based systems engineering? And also, how do we make sure that the organisational culture for these new UAS systems and operators, how do we make sure those are right? They have the right kind of aviation instincts. And then moving more to the research agenda, it seems pretty clear that as you get more and more autonomy, you have to rely much more on things like simulation. People talk a lot about digital twins. I was talking to someone earlier, we both hate the term, but anyway, it's there. But high adequate fidelity simulations of the world, which in some cases will have to include simulating humans as well as simulating machines. And also moving away from this very deterministic V-model approach to certification. So you set a requirement, you break the design down into components, you prove each bit's met it, you build it back up, release it, and that's the kind of classic V-model, to something which is much more about a continuous monitoring of how well the system is working, and having essentially a continuous certification process that integrates real-world observations, real-world feedback. How do we do that? That research agenda, there's, I mentioned some of the local folk, I'll mention them again, so obviously Cranfield and Blue Bear and others are involved in an initiative, and Thales, involved in an initiative called DARTEC, Digital Aviation Research and Technology Centre. One of the things that initiative is doing is opening up what's called NBEC, National Beyond Line of Sight Experimental Corridor. So the idea is to open up an experimental corridor where you can go and play with UAVs and demonstrate the things that you want to do, but do it from a live airfield. The great thing about Cranfield is it's a fully certified live live airfield, but where actually you can afford to stop the air traffic to go and play with drones for a bit. I think if you do that at Heathrow or Gatwick, people might object. And then also UKRI have recently launched an autonomous systems research program. So this is about £33 million going into a hub and then several nodes to really push this agenda around autonomy, not just for air, but the broader autonomy agenda. Recognising very clearly that we're only really going to get this stuff to scale when people trust it and we can demonstrate that it is trustable. So this is a really important program. The winners of that competition should be announced in the not too distant future. Whoever it is, I mean, the shortlisted players are all very high quality players. So in a certain sense, it doesn't matter who wins, although I obviously hope the team I've supported wins, but it's going to be really important. The hub has a duty to engage with industry and academia and the public at large on this agenda. So there will be opportunities to get involved if you're interested, and I think it's a really important initiative. So that's it. I hope you found that interesting and thought-provoking, and very happy to take any questions.